Start sharing. Okay, that's records already. So we had a little break of 1 week in which I actually recalled how some part of the argument works for that statement
Could you close
about
the window, the Skype window that it's
yeah, yeah,
making
yeah.
this black thing? Yeah, thank you so much.
So about that statement about staying nodal. So today we are going to prove it, or at least see why it's true. And yeah, the topic is called tropical caustic, and this is going to be part one. So I'll tell you what it is in a second. So first of all, let me give this definition that we give in some of our papers. So we start with a convex domain with an non-empty interior. So this is not necessarily compact. So it can be a half plane or a cone or whatever, but so it's called admissible if it doesn't contain a line with a rational slope. And some people complain about this definition. It's not very explicit. So to amend it, I'll just tell you which domains are not admissible, and all other domains will be admissible. So the whole plane is not admissible. A half plane with a rational slope is not admissible, and a strip with a rational slope is not admissible. A strip is some region bounded by two parallel lines. So, and we don't like when these lines are of irrational slope. Next time it will be clear why we don't like these domains. But anyway, for admissible domains, we'll be constructing a specific tropical curve which sits inside of this domain. And yeah, this curve will be called the caustic curve. And in a
I
sense,
find this very interesting. I find this very interesting already. I don't think it's entirely obvious that there is no other non-admissible domains. I mean, you just said convex and not containing a line, and already you're restricted to these very linear things. Is the
uh,
proof hard?
no, it's not hard at all. It's just, well, I tell you one more definition which joins these two. A non-admissible domain is some domain which has no support functions with integer gradient.
Support functions with integer
Integer
gradient?
gradient, yeah,
Mm-hmm.
integral gradient. So that's the true definition that we want.
Well, I
Okay.
think about it.
Yeah, but having a rational line really breaks this thing. So you have whenever you have some uh, function, linear function with integer gradient, it cannot be positive on the whole domain because it intersects this line with a rational slope somewhere. So that's the
Mm.
argument.
Okay, okay.
So yeah, anyway, so we construct a curve, a tropical curve. Well, this class of curves called omecotropical curves, and in a sense, it's a curve which is inscribed in this domain. And this particular curve will be called caustic curve because it's some curve which is related to some wavefront, yeah, like in classical geometry. But I'll not justify too much the naming. It's just called like that, and yeah, maybe not even everybody agree that it's a good name, but yeah, I call it like that anyway. So, and meta theorem is that the modulo of this curve give you coordinates on the space of admissible convex domains. And this we will justify a little bit next time. That's just for your information. In a sense, this curve knows virtually everything, almost everything about your domain. And obviously, there are two exceptions. Yeah, I'll jump just two slides forward. There are two exceptions when this curve is really silly. When your domain is a half plane, then the curve is just empty. And when your domain is a strip, although with rational slope, your curve is just a line parallel to the boundary, going exactly in the middle and having multiplicity 2. Okay, but anyway, so these were two exceptions to this restriction. So we actually take our domains to be polygons, and not any polygons, but unimodular polygons for this talk. So I'll tell you just in a second what it is. First of all, a polygon for me, it's some intersection of a finite number of half planes. And here we will ask that all these half planes have rational slopes, so that we can speak about primitive vectors going in the direction of every side. And in every vertex, we ask that two such primitive vectors form a z-square basis. Okay, so and this is what we call a unimodular polygon. And from the toric perspective, unimodular polygons are moment polygons of smooth toric surfaces. But I will not speak too much torically in today's exposition. Okay.
Nevertheless, this suggests a relation between this C omega and the modular space of toric varieties that I've been talking about.
So about convex domains, I like to think as some generalizations of or non-commutative toric varieties, symplectic toric varieties. Yes. Now let me define the process, the mechanical process which defines this curve. So the curve will be made of some trajectories of some particles. And these particles are sent from the corners of our unimodular polygon, and we are assuming that our polygon has at least one corner. So that's why I also say that these two cases of half plane and the strip are exceptional. There are no corners, so these two cases are forbidden. So now for every corner of our polygon, we send a particle. All particles are of equal mass, and the velocity is equal to the sum of the two primitive vectors going from the corner in the direction of the sides of the polygon. So for example, if you have a rectangle with the horizontal and vertical sides, then diagonally you send 4 particles, and they start moving. And now we are interested in what happens when they meet. So, and when they meet, whenever two or more particles collide, we use conservation of momentum. So two things can actually happen. So one thing is that the momentum, the total momentum is 0, so particles annihilate. And other thing that can happen is that one more particle is formed, a new particle is formed, which compensates this momentum. And there are two rules. One rule is that the velocity should be primitive, and that makes it necessary to introduce a multiple mass. So sometimes particles which are formed have mass greater than 1. And here again, observe what happens in the case of rectangular. Those particles, after some time, they meet at the same time. And if you look at the momentum, how it sums up, for example, for two particles on the left, you see 1 minus 1 and 1, 1. It sums up to 2, 0, which is not primitive. So the mass of the particle should be 2, and the primitive vector of velocity is 1, 0. And same thing happens on the right, but with the opposite sign. And after some time, those two mass 2 particles meet exactly in the middle of the rectangle, where they annihilate. So you see in this example both both types of events. So creation of a new particle and total annihilation. And you see that the process stops. So, okay. So now I think comes the definition.
And rationality ensures that the process stops.
Yeah, that will be one of the things that we will be proving, that it stops. A priori, no. A priori, it doesn't stop. Imagine, so if your domain is compact, yes, it always stops. If your domain is non-compact, for example, how do you call it? A quadrant. So like positive. So if you have quadrant like this, you send a single particle and it goes forever diagonally.
Whatever.
So it doesn't necessarily stop. Okay. But anyway, so this caustic curve is the union of trajectories of all particles in this process. And the multiplicities of edges are exactly the masses of particles. Okay. So now, yeah, I need to tell you. So like that condition of conservation of momentum is exactly the balancing condition in tropical geometry. So that makes automatically C omega a potentially infinite, but nevertheless some tropical curve in this weak sense that it is made of segments. Segments have rational slopes. They might have multiplicities, and counted with these multiplicities, the sums of primitive vectors going from the vertices are zeros, which is balancing condition. So now a point of a planar tropical curve is called smooth. In two cases, if either it belongs to the interior of a multiplicity one edge, so all the points on multiplicity one edges are smooth, or if it's a vertex, it should look like this standard vertex on a line, so on a tropical line. So
So
there is
in the example of the rectangle, it's not smooth because the multiplicity was 2.
yes. Well, it's not smooth. Yes, for example, because multiplicity was 2, and also because the two vertices are not like this from the SL to Z perspective.
That's right. But also a question, just as a curiosity question, can one blow up that multiplicity and make it look like this in any way, or can one resolve the singularity? Not really, can we?
No, because morally, this tropical caustic curve is a degeneration of an elliptic curve. It's a rational curve, which is a degenerate elliptic curve. So it should be singular.
Okay. Okay, of
It must
course.
be, yeah.
Yeah.
But that's not a big deal. So like okay, we will tell yeah, now the big theorem A. It tells you exactly how not smooth, how badly singular C omega is. So first of all, in any way, so the process in a sense terminates because C omega has a finite number of edges and vertices, so the collision stops after some moment. So it can happen that we have this kind of behavior for non-compact domains, that some particles travel forever, but they don't meet. So what's also important, that all these particles, they stay inside of the domain. So C omega belongs to omega, and they actually don't touch the boundary afterwards. So actually the intersection of C omega with the boundary is exactly the vertices of omega. So yeah, here we are assuming that omega is a unimodular polygon. Now, yeah, to answering your question, how badly singular it can be. So C omega has at most one multiple edge. And this edge has multiplicity 2 if it exists. It can happen that there is no multiple edges at all. And then there is at most one singular point in this case, which in a sense is degeneration of this edge to a point.
Like for the
So
square.
for the square, yes, yes. Well, there are other examples. For example, a triangle, a standard CP2 triangle. They also meet exactly in the middle. But there, it's hardly can be seen as this middle point as degeneration of multiplicity to edge.
Yeah,
Okay.
yeah.
So let me introduce this local terminology. We call this multiplicity to edge or the singular point, the terminal locus. So it's the locus where the process stops. Okay. So it can be one edge, it can be one vertex, or it can be empty, as in the example of a quadrant. Okay. And this theorem A, we will be understanding at the same time as theorem B. So in the exposition of my thesis, and which migrated to some our paper, we pretend that we first proving theorem A and then proving theorem B, but actually what happens is that we are proving them at the same time. So we comprehending these two results in parallel. So this is one of the things that was really hard for me to understand, that it's like that, but yeah, it's reality. So we prove these things together. So this theorem B tells you that there is a very precise tropical polynomial f omega, which defines this caustic curve C omega. This tropical polynomial is the minimum of all support functions with integral gradient. Okay. Yeah. So we take, so for example, for the square, yeah, for the rectangular, it will be 4 sides. So, and so the f omega will be like minimum of and if you want to represent the plot of this f omega in the case of rectangular, it will be some kind of pyramid. Well, let's say it's a square, then it will be a pyramid like this, like a standard yeah, standard base four-gon pyramids. Okay, and in the sense of this theorem, the terminal locus that was discussed on the previous slide is exactly the place where f omega attains the maximum. And here already I want to make a very important point about this locus where it attains the maximum. Yes, it can be empty in the non-compact case. Yeah, but otherwise, if it's not empty, it cannot be something of positive measure. Actually, it should be either a point or a segment, maybe a ray. Because in this tropical polynomial, this is a
Yeah, that
tropical.
would mean that none of these planes is parallel
Yeah.
to the XY
So
plane.
in principle, a tropical polynomial can have a positive measure set of the maximum. But there, it will mean that a constant term dominates. So this is a tropical polynomial without constant term. So constant term means that we don't introduce the minimum of some constant which that doesn't depend on the point. Oh yeah. Okay. So now how we'll proceed proving these two things. We will analyze what happens when particles collide. And whenever something bad happens, something clearly non-smooth, we will be saying that it's the locus where f omega attains the maximum. So that's
Can I imagine that the particles are moving along these planes of the pyramids?
they are moving along. Yeah, you can.
Along the edges of
Absolutely,
this pyramid. Mhm.
absolutely. You can imagine that they move 3D, and this will be just introducing the time to the picture.
That's right. And then I'm forming this pyramid on top of the convex domain.
Yeah, absolutely. You can think in 3D, and that's actually useful. Yes. So an alternative version of stating theorem A would be saying that at any moment the particles form the vertices of a particle form of the convex hull of the vertices of the. No, let me say it. That the convex hull of the particles in non-terminal moment is a unimodular polygon. So this is an alternative formulation of this. Okay, now let's proceed to proving the stuff, the theorem. So we will consider the first collision. Well, maybe there are many collisions happening at the same time, but let's consider one of them. And take two colliding particles, and we assume that those are adjacent. So in principle, there can be many particles colliding at the same time, but we are taking those which are sent from the vertices sharing a side. And we draw this side vertically. Then there are three geometrically different positions for the other two sides, S1 and S2, adjacent to the side S. So either these two sides are parallel, or they intersect, their continuations intersect to the left from the side, so from the same on the same half plane as the particles meet, or the meeting of the particles, the point of the collision, is to the one side of the side S, and the intersection of the continuations of the side S1 and S2 are to the other side.
Or
So
equivalently, when you have the 3D picture, is that the two planes intersect above, below, or just at the point of intersection, isn't it?
which planes?
Well, there is a plane associated to S1 in the 3D picture,
Yes,
and a plane associated to S2 in the 3D picture.
yes.
And then this is in the 3D picture, they intersect above the.
I think you're right. Yeah. Oh, wait a sec. No, they necessarily intersect above, I think. Just according to the slopes. This always looks like a pyramid.
It always looks like a pyramid, just right.
Oh. Okay, so in the now it will be quick. So the cases of alpha and beta, you can prove them in not prove but analyze them at the same time, in the sense that in necessarily in these cases of alpha and beta, this point of collision P has to be the maximum. And now I explain why it has to be the maximum of the tropical polynomial. Yeah. So we define an auxiliary tropical polynomial, which is just the minimum of the three support functions, lambda s, lambda s1, and lambda s2. And we note three things. So first thing is that actually this f tilde is superior to f omega. It's greater everywhere, just because f omega is a minimum of some bigger number of tropical monomials. So if we exclude some monomials from the minimum, we only get a big expression. Then second thing that we note is that F tilde attains its maximum at the point of collision. And this is easy geometrically. So you just should imagine how the plot of F tilde looks like. So in the case of alpha, when S1 and S2 are parallel, then the maximum will be going along the middle ray of this thing. If we are in the case beta, then it's really a pyramid with a triangular base, and then the point P corresponds exactly to the peak of this pyramid. And finally, what we note is that F tilde and F omega coincide at the point P. Why is that? Well, because the trajectory before that moment of collision of the particle sent from the corner between S1 and S is where lambda S and lambda S1 coincide. Same thing for the other particle, which goes from the corner between S and S2. And so the point P is where all these three things, three support functions coincide. And also along the trajectories of these particles, exactly these support function are the value of F omega. And so these three things, they imply that F omega attains its maximum exactly at P. I think it's clear. So this is written nowhere. This is a new argument. I think this is more transparent than what was written before. So is it clear?
It's clear and it's very nice. Yeah, it's very geometric, very clear.
Yeah, so brand new. Okay, so what happened is that we, like in this case, we automatically prove the theorem A and theorem B because the first collision is actually almost the last collision or the last collision. We immediately go to the maximum of the pyramid, and then we are in this terminal locus, and it can be only either a vertex where all particles meet the global maximum, or it can be an edge which is parallel to S1 and S2. And that's why it has multiplicity 2, because the monomials have just are opposite for S1 and S2.
But
So,
whenever it's an edge, what you're telling me that whenever the maximum is an edge
yes.
of multiplicity 2, there must be two sides that are parallel.
And not necessarily. Well, in the unimodular case, yes, that's always true. Yeah, but yeah, there are more complicated non-unimodular polygons, even triangles, where you have this edge, but you don't have a pair of parallel sides. But for unimodular case, that is always true.
But it was a hypothesis that it was unimodular. Is that so? Is that right?
Yes, yes, yes. We are asking it to be unimodular for this talk.
So in the unimodular case, there will be two parallel sides if the
Yes.
maximum is an edge. So it will be an exceptional situation. Most often, surprisingly, the maximum will be just a point.
Yeah, in a sense. In a sense, you're right. But then it gets terribly wrong when you consider just general convex domains.
That's right. That's right. The non-simplicial case, we would say in toric geometry, in the non-simplicial case, that is the most generic case, then this is not true.
Yeah. But thanks, that's a great remark. Okay, now we go to the case gamma, and yeah, that's easy, but you should be focused. Like otherwise, it awaits understanding. So in this case, this S1 and S2 are meeting to the other side of the collision of the particles. So we draw the dual picture for the gradients. And yeah, so that's a dual lattice to the lattice we had on the left. And first thing we note from this just geometric configuration that the gradient of the side of the support function of the side S, so gradient of lambda S, is a positive combination of gradients of lambda S1 and lambda S2.
Yeah.
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 Yeah, that's actually what was the observation two. The observation one is that the gradient of this lambda S1 should belong to the line, because the of unimodularity condition at the vertex between S and S1. So otherwise it's not a basis. So if you want to complement the gradient of lambda S1 with some vector so that it is a Z2 basis, then this vector should belong to this line below. Otherwise, geometrically, you should say that the triangle formed by gradient of lambda S and lambda S2, this triangle should have area 1/2. Therefore, the height of this triangle should be 1. And this is exactly the condition of being on this horizontal line. Okay, so should I highlight somehow? So when I speak about this line, I tell this line, which I am highlighting right now. Then goes the second observation. The second observation is that actually we should be at this gray highlighting here, just because of the geometric picture that the gradient of lambda S should be a positive combination of gradient lambda S2 and gradient lambda S1. Okay, and now the last thing comes is that actually there is only one position in this ray which is possible for the geometric configuration to the left. This is the position surrounded with these pink or red circles, because all other positions to the left of it are not possible, because then the particles don't meet. Let me show you just two first examples. So if we are, so let me. So that's the desired place, this one. If we are to the left from it, then the particles just to the left of it, then the particles go parallelly and they don't meet. So there was no collision at all. If we are even more to the left, then the particles actually diverge. The distance between them gets even larger and larger. So, and more to the left we go, more it diverges. So therefore, going back to the previous slide, there is exactly one position which is possible for this geometric configuration when the two sides S1 and S2 intersect to the right and the collision of the particles happen to the left, so from the side S. And this is exactly the condition that the gradient of lambda S is exactly the sum of the gradients of lambda S1 and lambda S2. So we see that that's the only case possible, the only possible case. So now let's contemplate it a little bit more. So there are two things you can do. Like preparing these slides, I was thinking that it's better to explain it just by removing the side S. So in a sense, it means doing blowdown. So we can do blowdown, and since this is exactly, yeah, this configuration, or alternatively, we can consider afterwards the following pink polygon, which is also unimodular. So this condition of being the sum, it assures you that actually the gradients of lambda S1 and lambda S2, they form a Z2 basis of the lattice. So a new polygon formed by new particles is also unimodular. Okay, so that's almost it. The only thing left to take care of is to analyze what happens if more than one particles meet, and according to the same scenario. So the same scenario as this gamma case, the last case, but that there are more particles than two particles. Assume there are three, for example. Then you have this S0, S1, S2, and both the particle from S0, S1 and S1s and particles S1s and SS2, they behave as in this last scenario gamma. Then you have this configuration in the middle, this one. So you have the first parallelogram, and then you have the second parallelogram. And which means that actually these two points have to be opposite in this dual picture. And recall that this is 0, this vertex. And this sends us back to this alpha case, where we have a pair of parallel sides such that we have a point where our tropical polynomial is given by the minimum of these two parallel sides. So this is almost like the case alpha, where we consider now this new tropical polynomial, auxiliary polynomial, which is made of minimum of lambda S0, lambda S1, lambda S, lambda S2, and it attains maximum at P, and it's superior to F omega, and this new polynomial and F omega coincide in P, and therefore this P is again the global maximum. So if more than two particles meet, then it's a global maximum. So, and that's it. So now we've proven the thing. So yeah, I know it's very how to say it, hand waving, geometric picture like proof. But at least I myself, I'm convinced that the thing is true. That is not exactly the exposition you can find written anywhere. And
well, I think it's more clear than what is around. You know, it's a little bit more concise. I definitely like it.
Yeah. Okay, and so from this, there is a corollary that these non-terminal positive deformations of at most nodal planar tropical curves stay at most nodal. And this is the result we need for sand piles I was mentioning before. So non-terminal means that we are not facing squishing faces. So we are not going to the very end of the deformation. When we do deformation of tropical curves, we change the sizes of faces, and positive means that we only shrink the faces, so we get them smaller. Which in this minimum convention means that we increase the monomials. And at most nodal, in this local terminology, means that the worst singularity is a simple node. And let me just tell you one thing, how these things are related. When you do a deformation of a planar tropical curve by increasing a single coefficient, this is exactly where you see these particles. These particles arise as the trajectories of the vertices of the corresponding face. And so, in a sense, what we've seen during today's talk happens all the time when you deform tropical curves. So, and this polygon is just the face of the tropical curve. Okay.
When you say this polygon is the face, what do you mean by this last sentence?
Like a tropical curve decomposes, like the complement of the tropical curve is a collection of polygons. And
That's
being
right.
at most nodal actually means that all these polygons are unimodular. And
Okay.
and when you do a deformation of a tropical curve, what you do, you shrink a face of this tropical curve. So you make this face smaller. So for example,
But the parameter of deformation is integral in this case.
no, it's you just change one coefficient for. So for example, the typical example is
Okay. Mhm.
is like this, and here you have some x plus something minus x plus something y minus y, no, something, and y plus something, and here you have just something, just constant. And this is what you increase. When you increase it, you have these faces get smaller.
Right. And this is a real valued parameter.
Yes, this is a real valid parameter. And that's where you get the trajectories of these particles. The trajectories of the particles are the trajectories of the corners.
Okay. Now I understand your sentence. Thank you so much.
Yeah, and the node is exactly when one side of this face disappears. The collision of two
Fantastic.
particles is, yeah. And we've seen that there is only one local model for a non-terminal event, which corresponds to this blow up of the corner.
But so the polygon encodes the space of deformations of the tropical curves. What's going on?
I don't get your
Original
question.
polygon, the original polygon produces this. I'm just trying to understand. We have this original polygon, and then given the polygon, the unimodular polygon, you
Yeah.
get this one caustic curve, C
Yes.
omega,
Yes.
given by these trajectories. But these trajectories seem to parameterize the formations of tropical curves.
Uh, which parameters? So
Well, you just said that these vertices, here in the example of the square, you have all these possible pyramids, truncated pyramids until you get the pyramid with
yes.
the vertex at the top.
Yes.
So it seems that uh, naively, it seems to me that the curve, the caustic curve, is parameterizing a whole moduli of tropical curves.
Yeah, you're right. In a sense, this is the central fiber of a deformation. Yes, of elliptic curves. So what you see here in the picture is actually an elliptic curve, and then it gets deformed terminally. So and it acquires a singularity. All the
Yeah.
curves, all the curves in nearby are smooth. That's correct. Yes.
But somehow the polygon, the unimodular polygon that we started with, encodes this central fiber and its deformation.
Yes. Exactly.
That's just
Okay.
an interesting factor. It's
Yes, we can think this way. Yes. Okay.
very, very nice. So this is 18 of 18. So
Yeah.
I think we can all thank Misha for his very, very nice talk. I'll stop recording.